In this problem, we have a crank rocker mechanism where the crank is round with a radius of 0.5 meters fixed at center C, and the rocker is a straight frictionless arm AB. Observe that we have a pin at point B which is fixed to the edge of the crank and can slide in the slot AB as shown. If the circular crank can turn with a speed of 2 radians per second in clockwise direction, what is the rotational speed of rocker AB? I already drew a diagram here in the XY coordinate system, so I can set up relationship between positions of points B and C, and then if I write position equations, then I can take a time derivative and find velocity formulas. So basically, if you look at the mathematics of it here, we can write two equations, x and y, and then take two derivatives and then solve for the desired unknown. So let's see how we can set up these equations. Observe that x coordinate of point C is already 0.5. So I can write xc, which is equal to 0.5 meters. I can write this in terms of distance d and angles phi and theta. So I can write 0.5 as d cosine of phi. This is x coordinate of point B. Then I have to subtract this little distance to get x coordinate of point C, and that distance is minus 0.5 cosine of theta. Then I can do a similar thing for y coordinate of point C, which is already known to be the same as radius of the circle, 0.5, and that is d sine phi minus 0.5 sine theta. And that's actually phi, not phi. That's not an English letter, so I don't want to pronounce it as phi. So let's take a derivative of these equations. Observe that for the position shown, angle theta is 60 degrees. So let's plug in all variables and all numerical data and then deal with these variables. So I have 0.5 equal to d cosine of phi minus 0.5 cosine of 60, which is actually a number. Then the second equation, I have d sine of phi minus 0.5 sine 60. So then I can solve these equations and simplify them. Two equations, two unknowns, taking a calculator and simplifying these equations. I have d cosine of phi equal to 0.75, and if I simplify the bottom equation, I have d sine of phi equal to 0.933. Then I have two equations, two unknowns. You see how I can solve for them. If I take the second equation, the bottom equation, and divide it by the top one side by side, I'll have d sine phi divided by d cosine phi equal to 0.933 over 0.75. d cancels out. Left side is nothing but tangent. So I have actually tangent of phi equal to this ratio of 0.933 over 0.75. Then I can take inverse tangent to find the angle. So I have this fraction, which actually gives me phi as 51.2 degrees. Then if I plug this into either equation, I can solve for D. Then if I find the numerical value of D, it'll turn out to be 1.197 meters. So these are the numerical values of these two equations. So let's go ahead and take two derivatives of the two equations and see how we can find derivative of the angle, which is by definition angular speed, which is what we're interested in, the objective of the problem. So let's go to the next slide and continue. I'll copy the two equations from the previous page, which are, let's rewrite them here, and let's clean this a little bit. xc equal to 0.5 d cosine of phi minus 0.5 cosine theta. And then yc we had from the previous page equal to, this is actually 0.5 equal to, not times d, but 0.5 equal to d sine phi minus 0.5 sine theta. Observe that I don't want to use those equations where theta was 60 degrees. I want to first take derivatives, then evaluate at the given values. Otherwise, I would be taking derivative of a number which gives me erroneously equal to 0. So let's go ahead and take derivative of both of these equations. Derivative of xc is x dot c, which is equal to 0.5, whose derivative is 0. And the right side of this equation, observe that d cosine phi is a product, so I want to use the product rule of derivatives. Therefore, I have derivative of first d dot times second plus first times derivative of second. And recall, derivative of cosine is minus u prime sine, so I write minus d theta dot sine of, not theta dot phi dot sine of phi. Sorry, I confused phi with theta. Be sure you don't make that mistake. Then I have derivative of minus 0.5 cosine of theta. Derivative of cosine is minus, times that minus gives me plus 0.5 theta dot sine of theta. So if I do a similar thing with the second equation, I have y dot c equal to derivative of 0.5 is 0. Then derivative of this product is derivative of first times second, which is d dot sine of phi, plus first, which is d times derivative of sine, which is phi dot cosine of phi. Then I have derivative of this term, which is minus 0.5 derivative of sine is u prime cosine, so I want to write minus theta dot cosine of theta. Observe that at this point I can plug in the numerical values. So for the given angle theta equal to 60 degrees, theta dot equal to minus 2 radians per second. Phi, recall from the previous page we got 51.2 degrees, and phi dot is the ultimate goal of the problem. That's what we're after. D We found it from the previous page to be 1.197 meters, and d dot is the other unknown we're after. In other words, observe that in these two equations, d dot and phi dot are unknown. Everything else has a numerical value. So if I plug in the numerical values in these equations, the top equation becomes, becomes 0 equal to. After plugging these numbers and simplifying, I have 0.626 d dot minus 0.933 phi dot minus 0.866, and then the second equation becomes 0 equal to 0.797, this is 0.797 d dot plus 0.75 phi dot, and then I have plus 0.5. So I have two algebraic equations with two unknowns. I can simplify and solve them and find the two unknowns. So then let's see, if I simplify this equation, I get d dot equal to 1.382 plus 1.489 phi dot. And then plugging this into the second equation, I have 0 equal to 0.797 times d dot, which is what I just found. So I plug in for it 1.382 plus 1.489 phi dot plus 0.75 phi dot plus 0.5. So this last equation has only one unknown, therefore I can solve for it, and if I do the numerical calculation, I get phi dot equal to minus 0.825 radians per second. And the negative sign indicates that rotational speed of the rocker AB is clockwise. So that's one of the unknowns we can find. The other one, if I plug this into the d dot equation, I'll get d dot, but that is not what I asked for. So this is the rotational speed of rocker AB. Thank you for watching.